Done? Okay. So we're ready to start our final lecture for today before the real fun starts, but this will also be fun. It's a great pleasure and privilege for me to introduce the fourth foundational lecturer of this conference, Subhashis Ghosal. Subhashis graduated from the Indian Statistical Institute in 1995, and he's currently a distinguished professor at North Carolina State University, the Goodnight Professor. He's the world's premier expert in the performance and theory of non-parametric Bayesian procedures, on which he wrote seminal papers and a 650-page book for which he won the Groot Prize. He's our at least second the Groot Prize winner today. Subhashis has a wide interest in which he bridges Bayesian and non-Bayesian approaches. He has written on high-dimensional models, shape restrictions, image processing, functional data, and biomedical applications, among others. He also served our community in various ways as an editor of many journals and an organizer of conferences, and he was the chair of our Bayesian non-parametric section. Apart from that, he's also a great educator. In particular, he had already 30 PhD students who graduated under his guidance. Today, he will speak on a new approach to inference under shape or under restrictions, and the title of his talk is Immersion Posterior, Empowering Bayesians to Meet Frequentist Targets and the Structural Restrictions. Subhashis.
Thank you very much, Ad, for this kind introduction. Well, I owe a lot to Ad for whatever I am today. And what he didn't mention is that the papers, like he mentioned the book. I mean, Ad is, of course, a co-author. Thank you, the scientific committee, for thinking that I'm worthy of a foundational lecture, and all of you for being present today. So let's start. So this is joint work with many of my former and current students. Start with Pritish Vaumik. So this has several parts. One will about differential equation models, and that's where he did his PhD. And Moumita Chakraborty, she was involved with monotonicity problems in univariate. Present student Kang Wang, who is supposed to be here, but I haven't seen him yet. So this multivariate thing of the same problem and convexity. And there are others to somewhat lesser extent, Wenlishi, Indrabati, Bhattacharya, and Soumita Pal. And it's always a pleasure to acknowledge NSF and also Army Research. So, when I teach any Bayesian course, I always start by saying that this remarkable straightforwardness of Bayesian inference, the Bayesian mantra is compute the distribution of unobservable given observables. And these unobservables can be our parameters, can be latent variable, missing observation, or future observation. So everything taken by the same, done by the same principle, just compute this conditional, and that's just, that's a probabilistic computation. So that's nice, really, nothing can be better than this. And we need a prior distribution. Many times this is obtained mechanically, not really prior in the sense of the word. And once a prior distribution is proposed, the rest of the methodology is conceptually straightforward, no matter what you do. Of course, this computation has to be addressed, but it has been addressed very well, especially in the last 30 years or so. So we have really strong methodology with this Bayesian. Everything is obtained from the posterior point estimation, interval estimation testing, whatever you want to do. And it gives us automatic uncertainty quantification. All of these are great features. And even if you're not Bayesian, it's convenient to behave like a Bayesian. So it can generate sensible point and interval estimators. But what is good also becomes sometimes a liability. So the problem is that it's stuck in the framework. Other than the ability to choose a prior, there's virtually no freedom in it. So no modifications are allowed once you propose the prior. It's like a highway with no exit, just you have to start going on. So compare that with a paradigm also likelihood-based, the maximum likelihood paradigm for estimation, and the companion is the likelihood ratio test for testing. So often things go wrong, and then it modifies, like in for partial likelihood in Cox proportional hazard model. But Bayesians, they don't allow this kind of luxury. And that can be a problem. One is also not allowed to use a data-dependent prior, or even in true Bayesian sense, a sample size dependent prior within a strict Bayesian paradigm. So, and also another thing to point out is that even if you're not interested in all unknown parameters, you still have to put prior on them, like the nuisance part. So the best example I can think of is like regression with distribution of residual. You're not interested in this, and you still have to put a model and a prior. So, but nevertheless, there have been a few extensions of this Bayesian paradigm, most notably an use of improper prior, where we just use non-probability measures and then mechanically apply Bayes' theorem. This can be justified using finitely additive probability, but it may lead to some paradoxes, as we all know. But most of the time, this is considered as genuinely Bayes. It's notably absent in non-parametric Bayes, where I do most of my work. And then there is empirical Bayes. It's highly popular, and intention is to be objective in prior selection. But the double use of data may be an issue, especially when you look at uncertainty quantification, because there is an underestimation of uncertainty. There are many landmark frequentist methods that are empirical Bayes, like Gemstein. Then there is hierarchical Bayes, the alternative to, and this I'll consider as genuinely Bayes, except that you may use improper prior in this higher level. And data-dependent prior it's often goes unnoticed, unaccounted in prior elicitation, except when formally used as in empirical Bayes. So these are some of the extensions that we are used to, and there are some other perhaps a little unknown, so we'll talk about that in a moment. So this stubbornness, which we stick to this particular way of choose a prior and then only you can look at posterior distribution, nothing else, that may cost if you look at frequentist properties. So there's perhaps a very well-known example in non-parametric Bayes is a very discussed paper by Diaconis and Friedman in 1986. For this kind of a type problem, but it's very importantly pointed out that you look at the location problem for a distribution, you want to make inference on the location, and they assume that the distribution is symmetric, mainly for identifiability reasons. And they use the most popular prior there, the symmetrized Dirichlet in this context. But often the posterior for theta can be inconsistent. So, I mean, these things can easily go wrong. But the problem, the embarrassing part is that the problem is easily avoidable by a less stubborn Bayesian approach. And we'll talk about that a little later. The agreement between Bayesian frequentist uncertainty quantification is also a very desirable thing. But unless you have some kind of Bernstein-von Mises theorem, which is available for regular parametric models and in some non-parametric models in the routine regime, some modification of the Bayesian procedure is essential if you want some kind of agreement with this frequentist uncertainty quantification. Now, as I promised, I would talk about a few more modifications of the Bayesian procedure. One thing is, like, instead of conditioning on the whole data, you condition on a part of data. So you do that deliberately to take advantage of something like invariance, and certain things just is eliminated from the posterior. So one good example is a transformation model where not x, but some unknown transformation of x follows the model. And you're not interested in this transformation. So one way of eliminating that, if it's monotone, is look at condition on the rank rather than the data, and then it automatically goes away. So this is useful, for instance, in ROC, the binormal model popular in ROC analysis, or the non-paranormal model used in graphical models, and I have used in some papers. Then there's another technique, is deliberately misspecifying a model. You use a working model, like a normal model for a distribution, even if you don't really believe that. Then the third one is when you construct credible sets and you are interested in also frequentist validation. Often, especially in smoothing problems, what has been observed in a paper by Cox that, this is Dennis Cox, so the coverage of credible intervals can be low. But to overcome that problem, what you do is not just the basic credible region, but you inflate it by some certain factor, and then things can be put on the right track. So the other modification I'm going to talk about here is what we'll call the projection posterior, one of the main thing of interest in this talk. So sometimes the parameter space may have very odd restrictions, and putting a prior there, computing the posterior, and more importantly, analyzing frequentist convergence properties may be difficult. So example is like a vector autoregressive or ARMA process that has very complicated characterization. So what you can do in this context is, like, you embed this complicated parameter space in a bigger space, but no structural restrictions. So things are pretty simple, and suppose that the model is still meaningful in the extended sense. Then you construct a prior distribution on the unrestricted space. Often conjugacy would be available then. And so we'll call that the unrestricted posterior. Of course, it doesn't live in the right space. So what you do is you look at the closest point from an arbitrary theta to the right space. So this is obtained by minimizing certain distance. And then you look at the induced posterior, which we'll call the projection posterior, and denote this by pi star given d. D is the data. So this is the picture. So theta 0 is the target parameter space, which is complicated, and you embed in something simpler called theta. So the posterior draw, little theta, would be typically outside this target. So you look at the closest point, and so this becomes the induced measure. And this map is, we'll call the iota. So that's the projection map. So here you got, I mean, when you study frequentist properties, there's a trivial concentration inequality. So theta 0 is the true value that lives in the right space. And then the concentration of the projection posterior around theta 0 within radius 2 epsilon can be bounded by, sorry, it's the complementary 1 minus concentration within 2 epsilon radius would be bounded by the residual probability of the original, the unrestricted posterior concentration in epsilon ball. So it's not saying it's doing anything better, at least, I mean, this is a trivial inequality. In most cases, it will be doing better, but here we're just, it's a simple inequality that comes from the triangle inequality. So this just says that from the definition of rate, the projection posterior inherits the rate that the unrestricted posterior has. So, and unrestricted posterior typically can be treated very easily from conjugacy or some other means. So what is important, you might think that, okay, so you are still inheriting from unrestricted posterior, so, I mean, that could have been just used, although it doesn't live on the right space. But the important thing to look at is that this unrestricted posterior has good concentration property because the truth is in the restricted space, because that allows some kind of approximation by relatively simple spaces that has low complexity. So that's why the whole thing works. And conjugacy, or the general theory of posterior contraction, may be used to obtain the rate for the unrestricted posterior, and then you just inherit that too. We'll do this illustration in examples like differential equation models and shape-restricted inference, which would be most interest part. So I mean, this is certainly not the first time in this concept is being used. I mean, in fact, it probably goes even back, but I certainly aware of Lin and Dunson, who did essentially the same thing for monotone regression. I'm merely formalizing this and maybe giving some additional examples in this talk. And then we had some work with Pritish Bhaumik on ODE models, and then extended to PDE models with Pritish Bhaumik, Wenli Shi. And then with Momita Chakravarti, this is univariate monotone. And then we'll talk about other ones that come after this. So, and some of the later examples I'll have, I don't know whether I'll probably run out of time, and in that case, I might just drop those examples. So, but what we want to also talk about somewhat more general, generalization of this projection posterior, which we'll call the immersion posterior. So it's the same setup. So you have a relatively complicated parameter space restricted by some rules like structural restriction, as in case of monotonicity or convexity. And then you embed it in a simpler space, exactly as before. And then you specify a prior distribution on the unrestricted space, you compute the posterior distribution, and then you have a map exactly as in the posterior. But only difference is that now you no longer require that this comes by minimizing a distance. It's just some map, okay? So in the completely general setting, it's just some map, which we'll call immersion map, and then it's just the induced distribution. So that we'll call the immersion posterior. So projection posterior is a special case. And the projection posterior has an appealing property that if you, it's idempotency, that if it's already in theta 0, then it doesn't change anything. So, but why we look at this generalization? Because while a projection map with respect to an appropriate distance is really natural immersion map, but the restriction is unnecessary for the concept to be used. In fact, depending on the aspect we want to study, there may not be a natural distance associated with it. So this happens, for instance, if we want to study the posterior distribution of the function value at a point. So then something like L1 or L2 distance, global distances may not be appropriate. And it's also not necessary in this framework that it has this idempotency property. It's already on theta 0. I mean, this restriction is appealing, but it's not necessary. Or even theta 0 included in theta, that is not necessary. This map is defined all over big space, that is also not necessary. Rather, what is needed is that theta offers an alternative parameter space. We'll have examples where these things will be essential. It's just an alternative parameter space where p theta makes sense. And then you can put a prior pi on the alternative parameter space, and it has a computable posterior distribution. And what is more interesting to us is that this induced distribution would be can be analyzed theoretically to study its posterior contraction, coverage, selection consistency, etc. So this, but for a general immersion map, of course, we don't have that that concentration inequality, so we may have to just directly handle it. So in most situations, the family of measures that we consider is dominated. So the support of the posterior distribution is contained in the support of the prior distribution. So all you do is you construct the prior on the right space. So what we note is that the immersion map may be allowed to depend on the sample size, just like a prior distribution may be allowed to depend on the sample size. Even you can think of data dependence, although I won't really venture into it. It's kind of becomes a difficult issue because of the double use of the data. What is important to note is that there's no uniqueness in this. I mean, of course, it's completely general. So the main purpose is to achieve certain targeted frequentist property, so like coverage or rate. So this property will really guide the choice. So what works is what we'll take. And even if these two parameter spaces, theta 0 and theta coincide, the flexibility of having an extra freedom, right? So this may be useful. The original classical Bayesian posterior may lack that advantage. So we'll talk about that in a moment. So, so more practically speaking, at least in non-parametric setting, the prior distribution often is constructed through a sequence. And the sequence of spaces which like of differing complexity, and they are often called a sieve, and then you put a prior on that approximation. So let theta j be such a sieve, which is typically a finite dimensional subset, and then pi j is the prior at state j. Then the computation of the posterior in this space theta j often reduces to a finite dimensional computation, typically through conjugacy. So remember I said that the immersion map need not be defined all over the theta. All is needed is defined over theta j, because that's where the posterior is sitting. And it is often typical that the immersion map on theta j will have range in the intersection theta 0 intersection theta j. Theta 0 is the target space, so it becomes goes inside theta 0. So that's how it should be, because that's and if it's also subset of theta j, it doesn't take it outside theta j. That's how normally things will be. Then the computation of this immersion posterior will also involve only finite dimensional computation. So that's really important, because you want to generate from the posterior. And most of, pretty much all examples will fall in this category. So, so what is the contribution and some criticisms? So this provides an additional component in Bayesian paradigm, since the identity map is an immersion map. So the classical Bayesian posterior is, of course, a special case. Of course, this is certainly true. What is important to mention is that this is not just an arbitrary random measure. It genuinely comes from Bayes' theorem applied, and then you induce. So, so in particular, you can take into account any prior information you had. You can really put in this. And then the additional flexibility may help achieve posterior contraction, frequentist coverage, model selection, consistency, or something that the usual posterior may lack. So let me tell story and relate to that, how I relate it to. It's a novel by well-known author in my native language, Bengali. So it's the story, and this was made a very popular film by one of the very most popular hero all time. So this was about, the story was about, like there was in a certain kingdom, there was a king who was all the time drunk. And so the villain, who was the king's brother, abducted him. But the minister found a body double, and he turned out to be a much better ruler. So it's like that. So the original thing may fail to a certain extent, but then you provide an alternative that just works. Okay, so and there may be some automatic model robustness. So we'll see, especially in differential equation models but the question is, how un-Bayesian is this concept? Well, I would say it's not as much as empirical Bayes. And so it satisfies the likelihood principle, for instance. There's no double use of data. And it gives a genuine probability assessment of uncertainty quantification. But of course, there's the sequential updating does not hold. So, there are, of course, it's not exactly the classical Bayesian posterior. It doesn't correspond this to a particular prior, but it's kind of, and the non-uniqueness is, of course, an issue, but the good choice should be guided by frequentist properties. After all, that was the goal. So now let's revisit the Diaconis-Friedman problem. And I told you there is very simple solution. So, and actually, a solution was all automatically, immediately pointed out by discussion of this paper by Doxam and Lowe. So what they looked at is just conditioned on the median instead of conditioning on the whole data. And then their setup, they didn't restrict to symmetric, which is, I don't think is essential for this problem, except for identifiability. And what they showed, but this required some analysis, that you get you put a digital posterior, and then it's not supported, but on symmetric distributions, but it works. Like it has a root and rate of convergence, unlike the original posterior, which barely has consistency. In some cases, it doesn't have. But I just point out that there is even a simpler solution which doesn't require even a proof. That is, you look at an immersion map from F to theta comma H star, where theta is the median, and then H is the shifted to median 0, and then you symmetrize. So this immersion map, you look at the induced posterior, theta's posterior is root n consistent, and even and we achieve also symmetrization as Diaconis-Friedman wanted, and it also has root n convergence. You also have a Bernstein-von Mises theorem. All this comes immediately and free. So the problem is easily solvable if you can just look beyond the typical setup. So how much time is left? So this is where I would essentially start my examples. So differential equation models. Sorry? 25. Okay, let's see how much I can go. So it's just a nonlinear regression model, but the regression function doesn't have a specified functional form. Instead, it's given by certain differential equation. In one variable, it's ordinary differential equation like this. More generally, in ODE model, you can have higher derivatives involved. In PDE models, you just have mixed derivatives involved. So they're just differential equations solution. So you can do a projection posterior very easily in this setup. You just embed this in a non-parametric model. And then in non-parametric, we have well-known priors. So for instance, basis expansion, and then you put prior on coefficients. So B-spline is a very popular one for good reasons. And you put prior on beta, just put normal prior, it gives conjugacy. And then you look at projection map for any function to the minimizer of a functional R, which is defined through some distance. So here it's a type where it should be a first derivative. So basically, it's difference between the first derivative and what is supposed to be under the differential equation model, and W is a weight function. So there's no numerical solver needed here. You just, you have the left side is coming from non-parametric model, and then you do this optimization that gives the map. So the if you generate, that gives you the minimizer, which is this psi f, and that induces the posterior. This is called the basic two-step method. Basic because it doesn't give the efficient concentration. You can achieve efficient concentration by directly looking at the distance between the function and a numerical solver. In this case, you need a numerical solver. So these are just two different distance maps. Both cases, you have this idempotency property. So if it's already in the model, then it gives you the original theta. So what it does basically is extends the definition of theta beyond the parametric model. And then we have a Bernstein-von Mises theorem that says that root over n times theta minus theta 0 is asymptotically equivalent with a linearization of f. And from there, it follows that the posterior centered at a suitable estimator is approximately normal. And the covariance matrix is the same as the covariance matrix of the estimator. So this is what we call the agreement between Bayesian and frequentist distribution. So that gives rise to coverage of Bayesian credible intervals. So what is interesting here is that even though you started with a non-parametric model, you still end up with root n convergence. So that's quite interesting. So the key here is the ability to control the bias. So this is what is needed. Root over n times f minus f0 max square is little of n power minus r. That allows you to ignore the bias. And the reason why we need this function f to be sufficiently smooth is that what we want here is that we should not be using a lot of basis functions. But with that fewer number of basis function, you can make the bias small, provided it is sufficiently smooth, because then the B-spline approximation is better. So, but once it achieves that, there is no point in, no advantage of increased smoothness. So there is no such thing as adaptation, because you already get the right thing, root n rate. So generally, this will not match with the Fisher information. So this is not asymptotically efficient, but you can. This is very easy to generalize to higher ODs and PDs. For PDs, you look at tensor products of B-splines, and GLM can be also addressed at request. I mean, there's no normal conjugacy, but I had a paper long time back where it had this normal approximation for increasing dimension in GLM. So that can be used, provided you have sufficient smoothness of this. Efficiency can be achieved by looking at direct distance, but then you have to use numerical solver, which means it takes more time to compute. This also works for PDs if there is a numerical solver. Okay, so that's pretty much all about differential equation models. Now going to the more interesting examples of shape restriction. So shape restrictions arise naturally in many contexts. The common ones are monotonicity, convexity, log concavity, etc. So this has been empirically observed, or it can come as a mathematical consequence in some inverse problems. Ordinary smoothing techniques do not automatically comply, but shape restriction, like smoothness, also controls complexity. So we don't need additional smoothness once you have some kind of structural thing. So there's other things like K-monotonicity, which I'm not talking about here. So there is a restricted parameter space for sure. And so we can use this projection posterior, more general immersion posterior approach in this context. So what you do is you look at finite dimensional approximations here through step functions. And if you're looking at a regression function, you just put on step heights, you put a normal prior, which is conjugate. For density, normal is not right, but you can use a Dirichlet prior that is conjugate. There's no additional smoothing requirements on this basis. It's indicators are good for approximation. You can use higher order B-splines if more regularity is needed. For convexity, you will need that. So monotone projection reduces to isotonization of these theta coefficients, which can be computed by efficient algorithms like PAVA. For present purposes, it's sufficient to work with a deterministic J, but we can also work with a prior on J. So you can look at L1 projection. The L1 approximation rate at monotone function is 1 over J, and that's the approx bias, and then you match with the variability, so that gives you this rate, and then you optimize at J approximately like n power 1/3, and then you end up with the minimax rate. Fairly simple through this concentration inequality. For density, similar thing, this works and same rate. L2 approximation, unfortunately, is not so good, but you can be rectified by using unequal intervals, but then it becomes more complicated because you have to put prior on the locations. On the other hand, the L2 isotonization of a density is a density, which was not in case of L1 isotonization, but that can be actually renormalized and the concentration inequality will still hold. So this will actually not be a projection posterior, but actually an immersion posterior in this case. You can use this for testing. I think for sake of time, I would rather skip that to go to more interesting part. So look at the coverage problem. So coverage is like you look at a credible interval. Does it have coverage? So like does the coverage go to 1 minus alpha? And here I mentioned this paper by Dennis Cox showed that in smoothing problems, the coverage may be arbitrarily low. He had a very weird formulation, very difficult to understand, but Odd has a follow-up paper some 20 years later. Now we understand this really what's going on. So what about monotone regression with projection posterior in this case? So here is a theorem that you look at this notation. So for a function, you define this delta f star to be argmin of ft plus t square, and let w1, w2 be two independent two-sided Brownian motions. C0 is this constant with a and b some characteristics of the distribution given as follows. Little g is the density of x, and fn hat is the MLE. We don't really need the MLE, but it's for comparison. If the number of steps is lying between n power 1/3 and 2/3, then for every z, we have these three conclusions. The sieve MLE has a limit. It's exactly the same limit as the ordinary MLE. Then for the Bayesian, the projection posterior, it also has a limit centered at the truth. So it goes to essentially the same thing, except that W1 is replaced by the sum of W1 plus W2. And the unfortunate part of this is that there's no Bernstein-von Mises theorem. If it's centered by the estimator, then this does not converge in probability. But we'll see that this is still useful for coverage. And this key tool in this theorem to prove is the switch relation that relates the isotonization with certain, the integral of the function with argmin of this. So this allows us to convert probability statements of f star in terms of the integral of this, and then we can handle that. Now this distribution of this random variable is known as the standard Chernoff distribution. This is also Chernoff, but because of double thing, it's just a scale Chernoff. So we just noted that there's no Bernstein-von Mises theorem, but that's not the end of all, because Bernstein-von Mises theorem is really not necessary for right coverage. What we have is like this, that this is very simple. You look at the equal tail quantile intervals, then the true value belongs to that interval if and only if the posterior probability lies between these two. Now, we have a weak limit for this posterior probability. Namely, you take this to this side and multiply by root n. So this converges to this thing with z equal to 0. But because z equal to 0, something magical happens. You see, here, if z is 0, so it doesn't matter what this C0 is. And C0 is an unknown quantity, so it just disappears. And it's a completely known distribution. What is true is that, this coverage would be the right one, that is 1 minus gamma, if this had uniform distribution. But this doesn't have uniform distribution, so it's something different. But it has a limit. So this nuisance parameter vanishes. The j has to be slightly larger than the optimal j for L1 constraint. So then what? Okay, so we'll call this random variable having this ZB because of its similarity with the Chernoff distribution, and it appears in the Bayesian context. We'll call it the Bayes-Chernoff distribution. Its CDF can be obtained numerically. There is no unknown parameter, and we tabulated it in our paper. It's very close to the uniform, but it's not quite. So it's symmetric about 1/2. What is also interesting is that it has slightly more concentration than the uniform in the middle, which means that the limiting coverage is higher than the credibility, which is exactly the opposite of what Cox found for smoothing problems. So for instance, to get a 95% equal tail credible interval, if you take 95% credible interval, it gives you coverage 96.4. Is that a problem? Yes, it is a problem because we are statisticians, and what is a statistician? Wants to be wrong 5% of the time. Okay, so, but I'm kidding, this can be easily achieved by a simple recalibration technique. So this is just, you start with a different credibility level, which can be explicitly computed, and then you attain whatever coverage you want. So, want 95% coverage? Start with 93.2% credibility. That's it. For density, exactly same story. And it also works for this, what is called regression quantile, the same story. How much time? 10. Oh, I'm doing great. Okay, so multivariate regression, so we want to also generalize this, but multivariate is always a lot more difficult than we anticipate in the beginning. So multivariate monotone means this this is the standard notion that it's monotone in every coordinate. Okay, so but conceptually very similar, so you use hypercubes and then step functions. And then monotonicity is a restriction to this convex cone in terms of coefficient, just as in the case of univariate. So L1 approximation rate is 1/j. Well, remember here, number of basis elements is j to the power d, so it's not quite as good as the univariate. And L2 is watts, as before. So we'll concentrate on L1, and the L1 contraction rate by matching the bias and variability will be n to the power -1/d plus 2, based on conjugate normal prior. Here's one point to note is that the L1 projection the theoretical projection is like using the distribution of the predictor, but you typically don't know that. So what you can do is empirical L1. But the interesting thing is that even if you use a different metric for projection and you want to study under a different metric, it still works. So that is useful because otherwise this would have limited applicability. And density case can also be treated as in the univariate case. So what about coverage and what kind of theorems we can get for coverage of fx0? So what turns out that the projection approach does not lead to optimal rate, and this is true even for empirical estimates. So instead we consider a map, so that means we'll look at an immersion map, not a projection map. So which is given by this maxi-min operation. So you look at the function over average over certain block, and then you take minimum over certain things and maximum. So this comes from the suggestion comes from the corresponding empirical paper by Han and Zhang, where they use similar operation, but their case it has continuous domain, but we have a discrete domain, so operationally and computationally this is a bit easier. So here is the picture which explains what is going on. So the left side, if we use the projection, so that would be like taking max and mean over this blue region and the red ones, so all possible such. But whereas the maximin is just over this kind of more regular region, so it's a lot less, and that makes it much more tractable. And well, you could have switched their order and then what you call get another immersion map, or both are asymmetric, so you make them symmetric by looking at their average. So all three are reasonable immersion maps, and we can look at the corresponding induced distribution. So for a sample of fx0 from the posterior, the unrestricted posterior, the corresponding mapped values are these. So their distributions are the induced immersion distributions. So in the univariate case, all three are the same, and that agree with the L2 projection, but multivariate is different. We have certain technical assumptions, essentially at that point how many derivatives are non-zero, so that, so that regulates the rate. So skipping the technicality, so this requires the function to be approximable by a Taylor's expansion. Then let's go to the description of the limit. So let H1, H2 be two independent Gaussian processes indexed by the 2D dimensional 2D dimension. So that is a deviation from the univariate, where we have there it was just there it started with one-dimensional Gaussian. Here, even if you use this for d equal to 1, this would be two-dimensional Gaussian. So the kernel is given by this formula where, and then you define two new processes, one process that is obtained as some kind of combination of these two independent Gaussian processes, along with some drift term. And then you look at the sup inf or inf sup of this, so call them z upper star and lower star. Then the limit can be described as follows. So here we're looking only at the limit of the posterior, the weak limit of the posterior. So let's just look at one, the others are similar. So this is the distribution that z star less than equal to z. So like that Charnov distribution. Well, of course, it's not Charnov because it comes from a different. So let's look at some spatial cases and see whether we have this univariate-like phenomenon. So that happens, and for that, what we need is that it comes out as a scale parameter. Then at 0, this will just disappear. So that happens under certain situations. So this essentially means that certain derivatives just vanished, and in direction k, there are this beta kth derivative is the first time it's non-zero. So under this situation, this simplifies, the limit simplifies. It can be written in this way, where H1 tilde H2 tilde two independent centered Gaussian. But now this is universal kernel. It doesn't depend on any aspect of the distribution. So this happens, for instance, this numbers relatively primes more. I'm more interested in the case where all of these are 1. Of course, that is satisfied. The univariate, of course, is a special case. So in that case, you have coverage of credible interval. It's given by asymptotic coverage. I mean, this is taking the role of the Bayes Charnov random variable. So again, it's not uniform, so it's something different, the limit. But interestingly, this is universal. There's no unknown parameter involved. So you can play the same game before. You get, you know what is the limiting coverage, and then you can correct it to the right. So this is from preprint we have, I have with Kang Wang. He will present, or hopefully will present a poster, so where you can see more technical details there. So the same story. And density, it also works. Do I still have some time? Not really. Okay, so anyway, the rest of the thing is less developed, so I will not go into that. So we can handle convex regression using the immersion map, and then also can apply use it for the entire distribution under stochastic order. And finally, we can also use it for high-dimensional models in sparse linear regression. But these are still not very well developed, so hopefully we'll show sometime later. So that's all. So thank you for your attention.
Thank you for a very fascinating talk. I'm particularly, well, I have one general and one more specific question. The general question is regarding the choice of or finding the parameter space theta where you are going to use that map. I forget whether it was theta naught or theta, one of the.
Theta naught is the restriction, and theta is something you
exactly.
use as a surrogate.
Right. So how in modeling, general modeling situations, how difficult could it be to actually try to work with that restriction? And then I will ask the second question also in the interest of time, if you can comment on it, particularly with your OD-PD applications. There's a big community in statistics, including, for example, Adrian Raftery, who's sitting here, which is called Bayesian melding, where they basically try to learn the parameters from physical processes and data. I was not sure if your method is actually going to be able to provide estimates for the parameters inside the ODs and PDEs, posterior distributions of that, or are they being treated as nuisance parameters and you're only concentrating on the fit of the model? Thank you.
Okay, great. Thank you for the question. Yeah, in most cases, well, not all cases, but in most cases, this comes, especially when you are using a projection posterior, it's kind of obvious where you should embed into. So for example, in differential equation models, you embed in a non-parametric regression model. Or in monotone regression, you just give up the monotonicity. So that's fairly simple, but in some examples it could be, you have to be rather imaginative, and so example is convex regression. I didn't have time to show the example in detail. So we can have a kernel-based, it's completely entirely different space where you put the unrestricted posterior and then use an immersion map through interpolation formula. So those things are a little, it's not too difficult to think what you should do, but that requires a little more thought. And regarding your second question, yes, we do get this distribution over theta, that the parameter of the ODE model. So it's concentrated in the space that you want. That's by its construction. And there we have this uncertainty quantification validated by frequentist benchmark. So I guess that's, I'm not familiar with that literature, so maybe I didn't answer the question exactly, but yeah, you get that distribution over theta.
Very nice talk. So I just have one maybe naive question. So your technique seems like only depends on the conjugate priors. So can you generalize those theorems to non-conjugate priors as well?
Conceptually there is no restriction, but if you want to study coverage, and I think that is what we are mostly interested in, because that's the difficult part. Then conjugacy helps a lot. So if conjugacy is somehow possible, it would not be smart to avoid that. So, I mean, that's what I go by. So
I think the question comes from, for example, the high-dimensional model.
yeah.
Like it's been shown that the non-conjugate Laplace prior can be better compared to the normal prior. So that's basically where my question came from.
That you are thinking in terms of the traditional Bayesian framework, but here we are using a different machinery. So there you can put conjugate prior, and then you use some kind of sparse projection to generate the target, the induced distribution that has completely different, it's completely different scenario, and we can actually prove quite a interesting concentration properties and selection properties, and all this we can derive using conjugate prior.
I see. Thank you.
Yeah.
Thank you. I think that's where we close the session, and we are ready for the reception. I'd like to thank Subhashis.
Thank you.